Yes, anybody have any questions? Julian, thank you.
Back here, I got a million notes from you. Thanks for that. Oh yeah, you said if you take a volume of air, right, and then you decrease the temperature, the humidity level in that goes up.
Yeah.
Okay, now I'm thinking that there's more warm, or I guess moisture in warmer air. But
right. So if we took that volume of air, and it had a fixed set of moisture in it,
okay,
when we decrease the temperature, it can now actually hold less, which causes the relative humidity to go up, because relative to how much it can hold at lower temperature, that would increase. Warm air can hold more moisture than cold air, so typically hot air masses do have more moisture in them. And if you take that mass and you capture it, you start cooling it down, the moisture is going to come out. Where it comes out is 100% RH, and that's the dew point. Okay. So what we worry about is creating those cold surfaces creates high humidities. Because what was a low humidity before sees that cold surface, becomes a high humidity. So what was 35% relative humidity inside your house, as it goes through that wall in the wintertime and it gets to colder surfaces, if it starts getting around 35 degrees Fahrenheit, it's up to 100% humidity. And that's when it starts to condense.
And is that kind of what you were referring to when you were saying there's relative and there's absolute?
Yeah.
So
yeah, absolute is that chart of inches of mercury. That's a measurement. You can sit down. It's got nothing to do with temperature changes. That actually tells you what the mass of water is. Now you know how much water is present. Now you know what temperatures you can live with. So that's absolute humidities. And that's actually where all the simulations on calculators are done in absolutes.
I did have one more than nobody else. Double vapor retarders, I know you're talking about basically from the inside then to the outside. You don't want to have that because you can trap moisture inside.
Right.
But we've been told that you can have vapor retarders right next to each other.
Yes. You can have side by side, right. What you don't want is you don't want water getting between the two. So if you have two materials that are resistive and they're actually adhered to each other, or they're side by side, there's no way for water to get in between, you've essentially got one resistive layer. What we worry about is when we split it, and now water can get in between the two. And this is the catch-22 of using OSB or plywood sheathings. The building code gives you very specific instructions about how to measure a vapor retarder. It never tells you to measure your sheathing. If you measure your sheathing according to the building code, what you find out is, oh, I got bad news for you. If you're using OSB or plywood, you're using a vapor retarder. So if you use OSB or plywood in a house and you use an interior vapor retarder, boom, you've broken a cardinal sin. You created two vapor retarders with a big space in between where water's going to go. How's the water going to get in there? Well, every window sold in the United States is allowed to leak from the nailing flange out. It's leaking right on the face of your OSB, where your OSB is cut at your rough opening for your window. It's getting right back now between the vapor retarder OSB and the vapor retarder inside. Again, we're the only ones that have a solution to that dilemma, the smart vapor retarder. The membrane product is a continuous sheet, or the dry right as a bat. That can live with it, because if the water gets in, it opens up. But yeah, two side by side, as long as water is getting between the two, you're fine. It looks like one. It's when you separate them and get big space for water to get in, that's our sin. We don't.
Why would you do that? I would assume if you have like a craft face bat, your stud facings are exposed. So at that point, I guess there could be a moisture issue. But if you put poly on top of all of that, then it covers everything.
This is it. Yeah, this is one of the. Yeah, that's a real big misunderstanding, especially among code officials. If you look at a craft face bat and you hold that bat, right, the vapor retarder is not the paper, not the craft paper. The vapor retarder is the asphalt on the fiberglass. The asphalt only goes from side to side on the fiberglass. The stapling flange is just a piece of paper. Whether you staple to the side of the stud or the face of the stud doesn't mean a darn thing, because there's no vapor retarder on the paper. With craft face bats, you've never had a vapor retarder in front of the studs. But that's okay, because the face of the stud doesn't need a vapor retarder. Because vapor retarders, studs, wood only picks up moisture at the end grain, which is occurring when the stud is cut. The face of studs never needed it. It can't absorb moisture from the air.
So what's the point of putting poly across the craft face bat?
What it gave us was, it gave us an interior air barrier. So we didn't realize we were doing it, that we were getting that. We got that. It hurt us in a lot of ways because it's too low a permeance. 1 U.S. perm is a vapor retarder by the old definition. A craft face bat goes from around 0.7 U.S. perms up to about 3 U.S. perms in high humidity. It's right around that 1 range. Poly is 0.04 U.S. perms. It's not a 10-fold, it's a 100-fold difference in performance. It doesn't breathe at all. The only place that stuff belongs in a building is below the basement slab. to prevent moisture from coming up into the concrete or breathing ground moisture up. It's got no business being on the walls. It never did. It was a big mistake we inherited from Canada. They got burned by it horribly 15 years ago. The class action lawsuits in British Columbia against condominium projects that have polyethylene in it are notorious because in Canada you can actually sue the government. So they sued the building code, they sued code officials, and they cleaned their clocks. And we still use it in places like Minnesota and the upper Midwest. For some reason, we inherited this really bad idea, and we never paid attention to what happened afterwards. We're seeing it now. Minnesota has massive stucco lawsuits now, and polyethylene is being pointed out as being one of the culprits because when the stucco was failing, the moisture couldn't dry to the inside through the poly. So really, it's a pretty strong position to say get rid of poly in your walls. Building scientists out there like Joe Steebrook, who is legendary in the industry, Joe preaches that you should, he wants all poly off the shelves, period, because of how dangerous it is in our walls.
Except you're saying in a basement against the block
wall? No, below the slab. Not in the walls, below the slab.
Okay. Oh.
Yeah, basement walls are really tricky because basement walls, the ground on the other side is 53 degrees. It's not that unfriendly to the inside. The problem becomes with moisture, especially when you have a walkout basement. If you got a basement that's partially below grade, typically the moisture drive there is going to be from outside in because the ground outside is going to have a higher moisture content than the room. So you get a moisture drive in below grade. And then everywhere your wall parks out above grade and it's wintertime, now in that part of the wall the moisture drive is from inside out. So what do? Do you let it breathe in and get terrible ice damage in the winter and frost damage in your wall? Or do you basically put up a vapor retardant everywhere and trap all the inward driving moisture below grade in the wall and rot the wall out that way? Darn it, believe it or not, we've got the only solution. Miracle, miracle. It's that same stupid product again, membrane, the smart vapor retarder. Solves that entire problem. Only product in the world that solves the walkout basement problem. Yeah. It's not an accident that we have that material, and it's not an accident that it does what it does. That is one of the most scientifically designed products on the marketplace today. It's an amazing material and solves a myriad of woes. And that was what it was created to do. Yeah, whenever you see issues like this, man, I know we're all at this quarterback concept now in the building solutions teams where we hear a problem, we pull in our teammates. When you hear about basement issues, when you hear about mold, when you hear about peel and stick membranes being stuck on walls, call your insulation guy. Get your insulation teammate on the ball because these guys are really heavily trained in the membrane product, and it is a no-brainer. The cost of the product, material-wise, is probably 3 times per square foot of polyethylene, which is saying it's a little bit more than free because poly is basically free. The good news is that installation-wise, it installs much faster than poly, so it's easier to work with, so your installed cost is actually lower. No other questions? Come on, Zeke. Yes?
So we're talking about perm rating between 5 and 10.
Yeah.
We're talking about exterior weather resistance.
Yeah. Yep.
Okay, can you go over that again?
Yeah, that layer of the building, I mean, typically, your house wrap, for lack of a better term, is really in the building code called the WRB, water resistant barrier. That's a layer of water. They lobbied to get the word weather taken out of their terminology at ASTM because weather implies that you can hold up permanently to things like ultraviolet light. None of those products can be left out for more than a year. I mean, a year is pushing it for a lot of them. So they wanted weather taken out of their name because they don't want to be around light. Ultraviolet light, which occurs just above your vision, wax plastics. They wax plastics. So a lot of those building wraps really get destroyed out there in the light. So they go water-resistant barrier, typically installed on top of the sheathing plane. Required by the building code in every residential construction built on a wood or a metal frame. Only place it's not required is built on block or concrete. Why? We let block and concrete get wet. We don't care. We put it there because 10% of the water is getting in there. But we want to be able to do some drying through it. We want to get some movement. We don't want to be an absolute barrier out there because if we are, any water getting past it is just doomed. If it can't make it to the inside, it's going to rot. So the level of performance for the water breathability, water vapor breathability, and this is not liquid water. These products will all hold liquid water like a bucket, but water vapor will still pass through them. The perfect properties that we found in general for different kinds of constructions and requirements is 5 to 10 U.S. perms. If you look at the CertaWrap product that CertainTeed has, it's not by accident it has those properties it has. Those properties were selected before the material was because those properties work best across the board. They give you the proper dryability and a proper resistance. You've got a good water resistance, you've got a great air resistance, and yet you will let some water vapor drive through at a slow rate to give you some drying potential. If you go too low, you don't breathe enough. You go too high, you breathe too much. That becomes really important when you look at the big market leader out there, say Tyvek. Tyvek is anywhere from 36 to 50 U.S. perms. That is very, very breathable. That becomes very important when you have a wall that has a moisture storage cladding. If the exterior surface of the wall can store moisture, every time it rains, it's going to do that. Every time the sun comes out, the sun's going to heat up that wall. It's going to evaporate that moisture, creating a very high humidity and temperature. At that point, a very high vapor pressure, which is then going to try to drive straight through the wall. How quickly it goes through depends upon the resistance of the layers in between. After it goes through the airspace, the next thing it hits is that water resistant barrier. It's going to go through that. So it's going to see 50 U.S. perms and go, woohoo, or it's going to see 5 and go, slow down. So that 5 gives you a really good balance. That 5 to 10 is designed to give you a good balance back and forth. Some drying potential and some inward resistance.
Where does that 5 to 10 number come from? Is that a range based on your personal?
Myself and many others. Okay. Yeah. So that is something I believe in wholeheartedly.
How would you recommend that a salesperson selling at 11.7 address that?
Well, 11.7, between 10 and 11.7 isn't worth talking about. The difference between 11.7 and 50 is worth talking about.
So 5 to 12 is really the ideal range.
If you want to put it that way, sure. Yeah, it depends upon the climate. Now, I can give you a given construction where 11.7 is the absolute best number you could possibly come up with. But all these things, you're trying to develop a product that works best in the variety of places that we're going to put it. Those permeances that we have are right where they need to be. And that comes from the computer modeling we do, the hydrothermal analyses, all the woofies, you've seen us run that stuff. It comes from that. It comes from running those and looking at the moisture balance of the wall. How wet do sheathings get? How much moisture can you tolerate? If you have a window leak, how much moisture can you dry out while not getting too much wetting or too much drying? It's a real balance. I mean, it's a living thing, these buildings. And so it's something I believed in the modeling for a long time. I know that it's my partner in building science at CertainTeed, Stan Gatlin, who also does a lot of modeling. He's believed this very strongly. We had these discussions a long time ago with DuPont. DuPont told us, quite frankly, they said, and this was off the board, and these aren't discussions that you can have with the customer, but just for you to understand where things are at. When we were down in Richmond, down where they make the product, I had a discussion with one of DuPont's physicists who I've had advanced computer modeling courses with in Germany. We've taken the same courses together and spent time and got to know each other. So I asked her, I said, Maria, why is Tyvek 50 perms? You got to admit to me right now that 50 perms is not a very good number. You would never pick this number. She goes, we didn't pick the number. The number picked us. I said, what do you mean? She goes, Tyvek's not a building wrap. It's an envelope. We happen to sell it in the building wrap market because it's very tear resistant and it's air resistant. But we didn't design it for a building wrap. It's designed to be an envelope. So 50 perms came to them, and they came out and said, it's breathable, it's great, it's great, it's great. And you ask them while we come off the side and say, listen, I can point to 100 constructions. Well, that's a really bad idea. They go, oh, yeah, I know. Now, you can't have that conversation with anybody, but that's for your information. That's the way it is. And they've done a fantastic job of marketing and selling it. They've showed us their curve on market acceptance of that product when they launched it against things like building paper, which was like polyethylene, practically free compared to the cost of their product. Very, very slow. And it was exponential. When it took off, it took off. How did it take off? The Tyvek experts in the field pounding it, pounding it, pounding it. So you've got to go out there now and kind of unsell something that got really well established. The fact is, science is on your side, and so is the rest of the market. If you look at every water-resistant barrier that's been launched in the last 5 or 6 years by any reputable company, they tend to be in that same range we are in performance. And it's not by accident. It's through extensive computer modeling and experimentation that we've all, people later to the game, have looked at it and said, you know what, there is a way we can improve this product. So the newer ones have done improvements on that property. So, I mean, that's the biggest one. But now you can get, it can be a he said, she said if you want to argue permeance with the DuPont Tyvek rep. Because they've got 10 years of marketing materials to throw it in your face why their number's the best. And all you've got is 10 years material to throw back at them. So it becomes a he said, she said. The best thing, though, is to talk, basically let the customer think about what you're talking about. Is there such a thing as being too permeable? Yeah, there is, obviously. So, and we can do the computer modeling all day long to show them which one works better. We've actually done this with customers in the past before we were in that market, in that game, selling that product, that part of the building assembly. and would show them how much money they were spending. Some people were spending 30, 40 cents a square foot out there on that installed material. And we were showing them that it wasn't performing nearly as well as something that was 10 cents a square foot installed was. And they made the change. Some builders actually made a change to get 30 cents a square foot back out of their wall and stick it into something like a higher R value, a better air sealing package, something to move that money around. Because you often, when you run a computer simulation at those permeances of that one market leader, that's not the stuff to be using. The building scientist Joe Steebrook ran around for 5-6 years just screaming bloody murder about that product, how bad it was for the walls, and they threatened to sue his pants off, and he stopped. And he hasn't said a bad word about him since, just under threat. But it's a lot of people don't like it. Yeah. So. Water resistant barrier, WRB, right there in the building code. Behind everything, even vinyl siding, 2009 on. Any state with 2009 code adoption, boom, has it in there. Builders must be using it.